In this next video, we are going to look at some statements that don't look like they have quantifiers, but they do have some hidden quantifiers in them. So we're going to look back at an old theorem that we proved that looks like an open sentence if you look at it in a shallow way, but turns out can be interpreted as a statement. And we're going to think about how we did interpret it as a statement automatically, even without thinking about it, as it turns out. And then just share some thoughts about implied quantifiers in general. All right, so here is the first theorem you proved in class. Let n be an odd integer, then n squared plus 7n plus 4 is an even integer. So yeah, we kind of proved this, or we had what we called a proof for this, but I got to point out some things that now might make you a little bit uncomfortable. First of all, that statement that makes the theorem, that has a variable in it. See that n? That's a variable. And you know, every odd integer we plug in for n makes it a statement. That's certainly true, right? 3n squared plus 7 plus n plus 4 is an even integer. Put in a value of n that makes it a statement, true or false. So it is technically an open sentence the way we have it written, which is not a statement. So then the question is, the uncomfortable question is, how can we prove it if it's not even a statement? We can't prove something that's not a statement. Statement has to be true or false. Well, here's the deal. If we think back to the proof, we assume that n was an arbitrary odd number, and we prove that no matter what that odd number n is, it always makes the resulting sentence true, right? So when we plugged it in. And if you think about what that really is in practical terms, really what we did was we proved a for all statement. So what happened is there's really a hidden quantifier in there that we weren't acknowledging publicly, but we kind of understood to be true. So here's the real theorem if you wanted to write it with the quantifier out there in the open where everyone can see. And that is, for all odd integers n, 3n squared plus 7n plus 4 is an even integer. So really that theorem that we proved it and we interpreted it as a quantified statement, even though we didn't say so explicitly. So here's some just general guidance for detecting hidden quantifiers in case this ever becomes an issue in the future. First of all, anytime you've got something that looks like an open sentence, seems like a statement, you're probably interpreting it as having a quantifier in there. So that either means you're interpreting it correctly, there is a quantifier in there and it really is a statement, or you're seeing a quantifier in there that doesn't exist in there. So you got to be careful about the context to see if you're interpreting things correctly. And then almost universally, that hidden quantifier is a for all quantifier. And yeah, I'm sorry, that was a pun, and it was intended, but I'm still sorry. So anytime there's a hidden quantifier, it's almost always a for all statement. So just look for that first. It's really harder to hide a there exists statement without making the theorem really weird. So you know, and why would you try to make it weird? So almost never would you find a there exists. If I think of an example, I'll give you one, but I don't even think I can think of an example where a there exists is hidden in a theorem. And when you're writing your own theorems that you're going to prove in your assignments, don't feel like you have to bring the quantifiers into the open for your theorems unless you want to. If you feel like I cannot write a statement now, a quantified statement with a hidden quantifier anymore, I can't do it, I have to do it, have to have that quantifier out there, that's fine. Go ahead and do it, but don't feel like you have to. So if you can't stand it otherwise, go ahead and put in the quantifier. Just be aware that they are there. That's the only important thing. All right. Now it's time for you to work on some quantified statements in context. That's what I call the problems. That's on the PDF file included with this video, and see how many you can get through.